Good morning, this is Deep Generative Networks, and this week we are going to talk about Generative Adversarial Networks, or we can simply call it the GAN or GAN models. The GAN models used to be the single most popular models for generating images until 2021. After that, diffusion models takes the place and become the most popular models for generating images. But you can still see GAN models here and there. So for example, if there's one of phase reduction models that is very popular in the stable diffusion pipeline. That is when you generate image from by stable diffusion models, and if you feel that the human face are kind of unnatural, you can use the face reduction models or face enhancement models to kind of fix the face in your images. So one of the popular one, or several of them, are the GAN models. And some of the models that can be work with the control net or other kind of stuff in these ecosystems that are still using GANs. But we can clearly see that GAN are not as popular as it was in 2020 or 2019. But still, if you are going to research or study how this kind of generative models work, generative adversarial networks are still very, very relevant, and it can still be a very useful tool in your toolbox if you want to design your own neural networks or architectures. Okay, so let's go to our lecture website first. So just as usual, you can go to the tjwei.tw and find all the related lecture notes and materials, course materials. And in this part of the lectures, we'll have a homework assignment. You still have like 3 weeks to finish these homeworks. But anyway, I will start to introduce a little bit so that you can prepare it early. So this homework consists 2 parts. One is DCGAN and the other is pixel to pixel. Both of them are ask you to do a task for generating images of human face. So for the DCGAN part, you can use DCGAN, you can also use WGAN and SNGAN, which we are going to cover next week. And the dataset are going to use is FFHQ. We're not going to use the full dataset, we're only to use the thumbnail part. The initial purpose of FFHQ is to providing high resolution human faces. So we are kind of against this purpose because we only use the thumbnail of these images. So the thumbnails are supposed to be low resolution. So in this case, the thumbnails only have 128 by 128 resolution. So because if we are trying to download the whole dataset, it is like 100 gigabytes. So it is a little bit toward the large part for a little bit too large for homework. So we are going to use only the thumbnail part. And besides, it is easier to do the training for a low resolution sense. If we are only going to use the handcraft DCGAN or WGAN. But you may find it is a little bit trouble to download this dataset. So one thing is 2 GB is a little bit large compared to some of the datasets like MNIST or facial MNIST or even CFR 10, CFR 100 maybe. The other thing is this image files are stored in Google Drive. Although you can see that I provide the repo, the link to the repo of this dataset, which is hosted by, the owner of this repo is NVIDIA. So this one is the official site for this dataset. And it provides a download script to download the images from Google Drive. However, due to the quota of the traffic, network traffic limitations, and this one dataset is a very popular one. So you may find you are not able to download the images from the Google Drive by using this script. So you can still using the web browser interface to download. But I recommend a tool that is Acron to download this kind of things. This can be a very useful tool to download file from Google Drive or other sources because it supports like 20 or 30 different platforms, like maybe Google Storages or like SSH, SFTP, or many different data sources. So it can be very useful for download dataset because nowadays a lot of datasets are really large, and so they are hosted. One of the popular choice is Google Drive. So you may encounter similar situation as we are facing right now. And Acron is a very good tool. So one disadvantage is it can be a little bit complicated to configure Acron to work correctly, especially if you are trying to provide your own Google Cloud API key for the Google Drive API. It is free. Google Drive API is always free part for Google Cloud platform. So don't worry about to pay or anything about it. Acron provide a shared or public API key, so you can actually configure it without providing your own API key. But if you provide your own API key, it may be download the files a bit faster comparing without it. So it's your choice. Maybe you can try it without your own API key first. Then you can try it if you feel you have free time to set up your Google Cloud account and other things, or to learn something if you haven't already familiar with Google Cloud platform. You may want to have like 1 or 2 hours to set up the account and set up the API and get the API key and do the setup and enjoy a faster download using Acron. But even without the custom or your own API key, Acron is still very useful and convenient tools. And I know a lot of people using it without using their own API key. So Acron is the tools that I use for downloading files. The other option is using GDOWN, GDOWN. GDOWN, currently I think it can support download files recursively from a folder. Although I still think it is a little bit unreliable, but it is a very popular choice, and we actually don't need all the images all perfectly. So if you are using GDOWN to download like 70% of image and maybe 30% of the image are corrupt or not downloaded, it is still fine. So if you are more familiar with GDAN, then you can use GDAN to download that. So anyway, after you download the images, the first part of homework is to ask you to train a generative model to generate a face image to 128 by 128. And the other part, the second part is pixel to pixel. So it helps you to pretty much the same thing, but as you construct the asset. So you can see a description right here. We're going to detail later, maybe next week. So right now, let's go to the main part of this lecture. That is, we are going to introduce the generative adversarial networks. So there are two papers that is important about this topic. One is the original GAN paper. It is titled Generative Adversarial Neural Networks. And the other one is DCGAN, which is Deep Convolutional Generative Adversarial Networks. This one is the paper that makes GAN popular, but most of the interesting part of this architecture, at least for theoretically or conceptually important, interesting part, are mostly in the first paper. However, the second part, DCGAN paper is still the contribution is still very important, because I think one of the important or tricky part is to implement. For GAN, implementation is a very important thing, because GAN is difficult to train and difficult to implement. So DCGAN actually provide the first work implementation for GAN that using a convolutional neural network. So what networks are using by the GAN, the original paper? It actually uses the simple MLP, multi-layer perceptron, which is just a bunch of densely connected layers of neural networks. So you can see that in GAN, it still uses some traditional examples for image generation, like MNIST or some black-white images. So the quality of generated things are not that good. And the DCGAN can generate some amazing images comparing to previous generative models. So you can find the links of these papers in our lecture notes. So this one is the images generated by DCGAN. Although some of the faces are still in the uncanny valleys, but overall you can find some of the faces that are at least some sort of convincing or realistic. This is one of the achievement by the DCGAN, because non-generative models can do such realistic generation. And in that paper, DCGAN paper, it also provides some latent working things to demonstrate the latent trend for a trend generator can be kind of meaningful. So this one is a simple demonstration for working from one latent to the other. The way it does is pretty simple. It generates two images by two latents, and by doing the linear interpolations of these two latents, it can transit one face into another. it actually shows that the latents are quite stable or usable. So one thing about the DCGAN is it actually generates some amazing images. In fact, in the paper, it actually has to write a description of this generated image to say these images are not taken from the training dataset directly. These images are generated. Although in our today's standards, we can see a lot of defect or non-perfect part in this generation. But considering these images are kind of small and printed on a paper or on a PDF, and back then, none of the generative models can generate such realistic images or images with that of fidelities, not even near. So it makes sense. It has some warnings to let people aware that these kind of images are actually generated, not taken from the dataset. Because that is exactly, people might mistakenly think these images are from dataset because it is just too real. Back then, it's kind of like if you are looking the image generated, the videos generated by Sora, and if you are already familiar with the SOTA video generation, you may still think that, okay, is this really a generated image? Or you may simply assume that it is a video to video generation, not or image, or maybe image to video generation, not a text to video generation, because it is just not good. However, a later paper, LScan, can generate even better image, maybe just one, like after 1 or 2 years later. So the typical usage for GAN is either like that unconditional generation, or like image conditioned generative models like pixel to pixel that we'll introduce later in this lecture. And this one is unconditional generative image for CFAS 10, I guess. And this one is generate a picture from the segmentations. And also you can condition by some labels, not by class. So this one is needs generation by conditioned by the class, by the label. So these are the typical tasks for generative adversarial networks. All of these works can be done by using diffusion models also. And this one is our works that generate different fonts from so you can create a new fonts from a few samples. That is also using GAN models. And in a DCGAN, it also provides an example for showing that the latent trained by GAN has some semantic arithmetic, like you can using latent for a smiling woman minus subtract a neutral woman and plus one neutral man, and you get a bunch of smiling men. We're going to detail a little bit later, but just so you know that a lot of application can be done even by the simplest form, the unconditional one. So you can still use in the latent space to do a lot of different tasks and tricks. So this one is manga or anime style images that generated using our models back to, I think, 2019 or 2018. I kind of forget, but it's definitely before 2020. So it has sort of decent qualities, but you can still clearly see that it doesn't generate hand. Not only just not good fingers, not only just weird fingers, it doesn't, in most of them, it doesn't even have fingers. So it kind of shares the same problem of the diffusion models, that it has a difficulty to generate people's hand. So in later version of this one, still using again, it can actually generate some fingers, but still it kind of like the early stable diffusion models. It will have the strange hand generated. But this one is give you a simple impression of how good or what I mean, when I say how good, is I'm just saying the level of the quality that GAN can generate. So it's sort of passable if you just have a quick glance. That is something very major and can be produced or generated from GAN models. And then later it can actually have more details. There are a lot of improvement on GAN, like CycleGAN, CycleGAN 2. It can actually generate a little bit better than this one. So what is the good part and the bad part for GAN? So the pro of the GAN is that it can be generated in parallel. This is compared to like PixelCN and PixelIN, and it has a very few restriction. So you don't have to model. It has a twofold. One is that you don't have to have a spatial property for the or assumption for the distribution for the things. It can fit to any kind of data. All you need is some kind of data. The other part is for the architecture. You can actually, I mean, at least in principle, you can have any kind of architecture, any kind of layer to construct your architecture. It's kind of difficult to train. But this is in contrast to generative flows, because generative flows needs spatial kind of layers in order to do the inverse backpropagation or to do the inverse layer. And the most important part is it produces good quality of images, at least compared to previous models. But one thing that is very crucial to limit its popularity for at least for now is it is very hard to train. Especially even if you have the semi-chemical data, if you wish to simply increase your data, you just collect more data, the model may be corrupt or doesn't converge that well. Even if you just only to scale up your dataset, you may need a different parameter, different learning rate scheduling. It may just right there, but whenever you just simply change your dataset to another domain, or just keep the same domain, keep the dataset in the same domain, but you increase your data like from 10,000 to 100,000, you may have to adjust your hyperparameters. So it may be very difficult to scale. So that's one of the key weakness of the GAN comparing to diffusion models. Because diffusion models is relatively stable for the scale of the size of the dataset. Okay, so let's describe what it is. It consists two parts. So basic part is the generator. The G stands for generator. So basically, it's just like other generative models that if you feed a latent is supposed to be random vector to some sort of distribution, or it's typically the standard normal distribution. But if you wish to change it to something else like a uniform distribution, it is just fine. You can still get some result. Maybe the quality has some difference, but it doesn't matter that much. So you can actually have any latent distribution you have, but typically it is just the normal distribution, at least for some on some domain. Okay, so then you feed your latent into your generator, and it is a neural network. Typically, it is just a simple bunch of convolution, transposed convolution. So first your latent gets reshaped into an image, like maybe like 4 by 4 by 32, or maybe something like, or 4 by 4 by 1 maybe. Then you use a transposed convolution to actually increase the channel and increase the size, a slightly transposed convolution to increase the dimension, and 1 by 1 it will become a large image, maybe like 128 by 128, and by 3 you have 3 colors, and you generate the images. Okay, so that's the generator. Pretty much you must have one generator, of course. So the thing is, it is very difficult to have a image quality assessment method to see, okay, how well is the image generated? Because if we wish to train this generator, we must have some loss function to do the backpropagation and do the gradient descent, and to make it to learn the results. As we have stated in the lecture of variational autoencoder, we need some, even if we have some reference image, we need a very accurate metric, like mean square error. So in that case, we actually say that there are two actual solutions. One solution is to do a more efficient sample, so we have a better estimation for the likelihood, and the likelihood is kind of similar to mean square error. That's what I meant. And the other way is to use a different metric other than the log likelihood. So we are taking the other way. We are using a different metric. And the other reason is we don't even have a reference images in this case. So we definitely need another way to kind of measure how good the result is, so that we can have a loss function. So in the study of neural network, we usually joke about that if you have some question or problem that is very difficult to actually write down the algorithm, you can replace the algorithm by a neural network. So that's the idea. We're going to replace the matrix by a neural network. However, how do we train this neural network? So the thing is, we only need to give a score, or we only need to give a score of how good this image is. We already have a data set that contains a bunch of images that's supposed to be the good images. All we need to do is to construct a data set of poor images or low quality images. So this all we need to train a discriminator or a classifier. It is actually a binary classifier that can tell which image is good and which image is bad. So if this image has a good quality or like a real one, we call it real, and we output maybe the number 1, or our output is between 0 and 1. 1 is the good, 0 is bad. Okay, so all we need is a dataset for poor images, but it is very difficult to control such poor images because first of all, we don't have 1, and we are not exactly knowing what kind of poor images do we need. Even if we have construct a dataset of poor images, the other issue is that the generator is a neural network. Neural network can always find a way to survive, to cheat. It's kind of like a genie that can grant you wishes, only that it grants you wishes in a terrible way. Like if your wish is to become the richest person in the world, so you are thinking about, okay, I'm getting millions or billions of monies, and so I can become the most richest person in the world. But the genie grant your wishes by making all other people poor, or even worse, making you the only person in the world. That was totally terrible. But technically, it is satisfy the statement of your wish. Neural will do that kind of things. If you have a metric pre-trained, even if a pre-trained to tell a bad image from good and a good image from bad, generator is likely to find a loophole to generate something that is terrible, but get a very high score. That is exactly what the behavior that you are going to expect that the generator will do. So instead, we actually let the generator to generate images, and using those generated images as the samples of poor image directly. So not only we can get our dataset for poor images free, almost free, and also it's kind of close the loophole for generator, because if it find a loophole, the discriminator will quickly adapt to consider this kind of loophole as a bad images. So that's why the discriminator might work. So all we have to do is, okay, the discriminator is how we train a discriminator. We let the generator to generate images, and also we correct the images, sampling the image from the training dataset, and we label, because we know where it comes from. So we give a label so that we know these generated images are fake, and we label these images are from the dataset are true images. So the task of a discriminator is as a binary classifier, so that it can class an image from the true to the false one, a real one to the fake one. I should say that. We can tell the real images from the fake images. So it is simply, effectively, and I actually just literally the task of a binary classification. So we know it is the most simple job for deep learning or neural network. It is sort of the easiest task for training a neural network, and we are expecting it to do very, very well and converge quickly. So okay, that's the discriminator part. It's not easy. So how does the generator work? So we train a generator in a way that we let the generator to output an image, and after it send this image to the discriminator, so we get a score of how good and how bad it is. So no matter how discriminator is training, the task for training the generator is straightforward. We simply maximize the score to be, because the higher score is when it is real, when the discriminator consider it real, and the lower the score is how the discriminator consider it is fake. So in other words, we are training the generator to kind of cheat so that the discriminator cannot tell the difference from the fake image to the real images. So that's the basic idea. So for the implementation, because the discriminator is a binary classifier, so the most popular loss function for the discriminator is the cross entropy, actually for the binary cross entropy. So this one is the standard form of the binary cross entropy. So for the generator to cheat the discriminator, we can simply use the same loss function, except the goal for the generator is to maximize the loss function. So the discriminator can not tell, because when the loss is lower, that means the generator can very effectively tell the difference between the good one and the poor one. However, since the goal of the generator is to cheat the discriminator, so the goal of the training goal for the generator is exactly the opposite. So it wants to maximize this kind of loss, the cross entropy loss. In other words, for a discriminator, when the x is from the real image, it wish to output 1. The perfect score is 1. So dx is equal to 1. So log 1 is 0. Remember that 0 is the large possible value for log dx, because the value of dx is between 0 and 1. So we have this one 0. And this one is negative. So it becomes a loss function, because smaller is better. So on the other hand, because we are minimizing this, so the best thing is, the best possible output of D is 0 when the input is the fake image or generated image. So if this one is 0, this one is 1 minus 0. So we still get a 1 here. And log 1 is 0. This one is the largest possible value that it can have by putting a negative sign here. So we get the smallest possible value. Okay, so this loss function is essentially direct the discriminator to ask it to generate the dx to be as close to 1 as possible, and dgz to 0 as close as possible. Also, that's it for the discriminator. For generator, this one doesn't really matter, because this part has no generator involved, so it can only take the second part. This kind of setting is interesting in many different aspects. Theoretically, it can be considered as a min-max game, in game theory. So these two players in a game are totally against to each other. One man's gain is the other guy's loss. So they are totally against to each other. So a lot of study have been done to this type of game. And this kind of game is kind of has certain properties to have a more optimal solutions. And also, which we will see a little bit in detail later, if we are training our models according to this kind of laws, theoretically, our model is going to minimize the JSON channel divergence. So if this one is the research or study you are working on, and at this moment you may think, okay, I'm hitting the grand prize, I'm hitting the lottery. Because recall that we are starting from a totally different motive. We're trying to simply replace the matrix with a different one using a neural network and doing so and that. And eventually we find out, okay, we are starting from somewhere not considering any kind of KL divergence or JSON channel divergence or other things, but we are getting something that is actually minimizing a well-known matrix to measure the difference between two distributions. And this distribution, and then this is actually our goal. We wish the generated image, the generated distribution is as close as the distribution of the data set. So one way to measure the difference between two distribution is using some kind of divergence. JSON channel divergence is one of the divergence that has some good properties. So this theoretical argument says that if we are training our model, well, our model can achieve the optimal in the sense that if we measure the difference between these two distributions, the real one and the generated one, by JSON channel divergence, we already achieved the optimal one. So that's kind of interesting. However, you will see later that in practice, we are not actually using this kind of we are going to change the loss function for a generator a bit. So all of these things are not valid anymore. So that's kind of interesting. If we are using the same loss function, we have very good theoretic properties. However, that one doesn't work very well in practice, so we change the loss function to another. So after we change the loss function, we don't have this good theoretic good properties, but we are achieving the success in real life, in practice, because we know that GAN has its glory time for quite a long time, and it can actually generate quite good results. So that's really interesting. We are teaching the formulas that theoretically good. Just change it a little bit, but in the result, it becomes very, very useful in real life. But before that, the idea of GAN is still quite interesting. So we can see this kind of diagram. The green one represents that the generated distribution, and denoted by the black dots the true images, the real images, or the target distribution that we wish to achieve, and the blue dash are used to denote the score given by the discriminator. That between 0 and 1, we give a score of how good it is. So you can see that because this is latent, this kind of showing that this one generate image right here, this one generate an image right here. So so you can see because it is more dense right here, so the green curve is higher at peak at this guy. So initially the discriminator is kind of random because it hasn't been trained yet, and the green curve is definitely different to the black curve. And after some training, the discriminator has because it is simply a binary classifier, so it can train really quick. So it will have some, we are expecting it to have some nearly optimal result. So you can see it is kind of have a good behavior right here. When the black, that is the real image, on the real image, it is more likely to be a real image. We give a higher score. And when it is more likely to be, right here, more likely to be a fake image, we'll give it a lower score. And the green distribution adjusts to getting a higher score because the higher score is on the left side, so you can expect that the green curve moving toward left. So after a while, the green and the green curve and the black curve coincide. Then the discriminator, the best discriminator can do is output something that I don't know, because it is just they are equally as good. So that's the process for GAN training. So in fact, we can actually derive the optimal discriminator result. It can be computed right here. You may think, okay, this seems to be almost impossible. How do we know what is the solution? If we already know solution, why not we just simply use it as the I mean, if we can calculate, we just calculate. We don't need to train the discriminator. The thing is, the P data is kind of a continuous version or the ideal version of the training data, because we know that the training data are taken from some distribution, but we don't actually have the access to the direct access to the true distribution. We can only have a sort of a sample to form our training data set. So this is suppose that we have a true distribution. So training data is not exactly the same as the real distribution of true images, real images. They are not the same. So just suppose we have access to that, but I mean, training data is the best we can have to approximate the real distribution. So it can be viewed as a proxy, or maybe the second basic thing we can do is to do the augmentation on the training data. So it might be more even closer to the true distribution for real images. But the fact is that we don't have. But suppose we have the real images, the true distribution of the real images. Let's call it P data. So the optimal of the discriminator is the result should be output something like this. This one may seem strange. Why do we even need that? But just simply consider, suppose you are the discriminator, you are the human one, you are the discriminator. When you get an image, how would you give the score of these images? So for the first thought, for the first glance, maybe you think, okay, let me really think about it. It might think a little bit easy, because if I am receiving a fake image, a generated image, I'll give you a real score. If I'm receiving something that from data set, or at least, because now we have infinitely many data in our data set, because our data set is the real one, the true distribution. So we have infinitely many, but still, because we are thinking about the optimal one, we're not consider about the efficiency. So we get this one, we can compare to the data set and to see whether this one is from the data set. Then we know it is true. we know it is from a true distribution. It is a real image. So we give it a score 1. So other, if we are okay, so my camera is out of battery. Let's go back to here. Turn off my camera. Okay, so so if we know it is a real image, we output score 1, and if it is not, we output score 0. As simple as that. So what's wrong with that? The thing is, we are consider about the distributions. So there are always no. Usually, in general, there are no 100% certainty of yes or no. So consider this kind of graph, curve of distribution. So for example, right here. Okay, let's go back. Okay, maybe I should use pen right here. Okay, we have a pen right here. So consider this straight line right here. So this is our x. By fixing one x here, although this one seems to be more likely to be the real images, it is not 100% because it has some small chance right here to be from the generated one to from a fake one. Same thing happens right here. Even at here, you can see that there's a small chance it is true. It is true from a true distribution of a real image. It's going to be a real one, but still some small chance, small but non-zero, In fact, even for this kind of case, we are thinking this one to be almost 0 for the green one. But it is a continuous distribution, so it has a non-zero chance, just like what we do for the variation autoencoder. We are adding a noise to a generated image to form a normal distribution. So every possible image can have some non-zero probability that is generated by our model. It just might be very, very small. So this one is similar. So no matter, so every image has some possibility to be a generated one, and has some probability to be a real one. So that is how we consider, and especially when the generated image is going to be more and more real. So we can see a lot of situations, especially you can consider this one. This one has 50%. If you are getting an image X right here, you'll consider giving it a 0.5 score, because half of the time it comes from the real distribution. the distribution of real images, half of the time it comes from the generated images. So the best thing you can give is 0.5. So in fact, if you do some calculation, you know that the optimal value that the discriminator should return is the probability that the given x is come from the diffusion of real images. So this one is exactly the value that I'm just mentioned. The probability of x, given we already know what x is, the probability of x is getting from a real image is exactly this one. So that's it. And after we get this formula, we got what the output the discriminator should have. Suppose this is the true value, and we are expecting it to be a kind of plausible or likely approximation of a real situation, because discriminator is usually very easy to train because it is a binary classifier. It is supposed to be easy to train. So we're kind of expecting our discriminator is doing very, very well. So this is kind of likely to be the real case. And if we suppose it to be exactly the real case, we can do the computation to compute the K diversion, or as I say, cross entropy of this kind of thing. And we'll find out it, in fact, this one is what we plug our discriminator into it, and we'll actually compute the loss function, like this one. And this one turns out to be exactly the Jason channel diversion. So what is Jason channel diversion? So first thing we need to notice is that KL diversion is not symmetric. That is, KL PQ is not equal to KL QP. They are in a different. They are different. And the other thing, the other poor property is that when Q is 0, but P is not 0, this one is going to become infinite. It's going to be infinite, so which is very bad. So for the first one, symmetric property, because we are measuring the distance, we usually wish from A to B and from B to A to be the same. So one way to do that is we do the KLPQ and KLQP and consider the average of them. So we compute KLPQ plus KLQP and divide them by 2. So that's one way to do that. But this one will make the other property more serious, because no matter Q is 0 and P is 0, then it will going to be infinite. So it will render this PQ useless. And also when P is 0 and Q is 0, because we compute KLQP as well. So in that case, it will become infinite. So that's not what we want, because we don't like our value to be infinite when we do the computation. And because PQ are not the same, so you may imagine that might actually happen a lot for the distribution that we are interested about. So another way to make it symmetric and actually solve the problem of infinity is we'll consider a middle point, a middle length between P and Q together. So we consider another distribution M, which is equal to P plus Q divided by 2. So this one is a random distribution that is, we flip a coin. If the coin is head, we use P to sample one sample. And if the coin is tail, we use Q to sample one sample. So that's the meaning of what P plus Q over 2 is. So have a chance we are using P to sample a new sample, random sample, and the other case we use Q. So this one is M. So we can compute the K divergence of PM and QM. So that is fair to be for P and Q because they are symmetric. They have the same rows. So this one make this JSD to become symmetric. And more, because M is the average of P and Q, you cannot have the situation that M is 0 and P is non-zero. Because if P at some point X, the P is non-zero, we at least we have half of the chance to choose P and sample that things from P. So MX cannot be 0. It will be at least half of PX. So MX is at least half of the PX. Okay, so that is why we don't want to have the infinite situation, the infinity issue for K divergence. Okay, so that's a generation divergence. So this is kind of a good K divergence is very, very popular. When we think about the divergence, we first think about K divergence because it's very close to cross entropy. And the Jason channel divergence is a good version, a symmetric and non-infinity version of K divergence. So it is a good divergence. So it turned out that our GAN architecture can actually train our model to minimize the difference respect to Jason channel divergence. And we can actually use this information to see how good our training is because we know the best we can get is negative log4. Like we have mentioned before, we are going to change the loss a little bit, but still, for a discriminator, we are still using exactly the same loss. So this one can still apply. So you can when you look at your training loss, it will make more sense to you because we actually those are not just some random numbers. We know something about them. They are not totally black box. They're still black box, but we know things about it. So these are some examples generated by the original GAN. Especially you can see that it generates black and white vase and it's cropped to very center of the vase. This is kind of usual for the time that GAN has originally published because people are still generating some easier data set. So this was one example for an easier data set. After that, we are trying to generate more difficult data sets. And the generated images are not that good if you see the following things. Still kind of mess up. Okay, I provide some code. Although they are a little bit dated, you can see that those are like 5 years ago. But still, it has a PyTorch and the TensorFlow implementations. You can see some architectural design. And for our homeworks, because like we mentioned that GAN is very difficult to train. So it is okay if you are looking for other people's implementation and their architecture. You just write it by yourself, but you can reference to other people's design. Because if you are not doing that, it might be a little bit difficult to make it work. So let's see some implementation details. So first, for a generator, you are using a different loss function. So this one is the original one. Whereas in a theoretical one, we are going to maximize this loss. However, in practice, you are not doing so. You are using this one instead. You are minimize this loss. The reason is the G is going to try to kind of cheat or the discriminator. So the goal of GZ is to output something, so that D will output 1. So 1 minus 1 is 0. Log 0 is become infinite. Like we just mentioned, infinite always makes some issues. So we don't want this one. We don't want. And in fact, when we try to actually do the training, this one is more unstable and difficult to make it actually converge. So this one is more popular. The later one is more popular and actually used in code. So this one is what we are going to use and to do the training. But the goal is still the same. We are trying for, I mean, at least for a generator, we are trying to make some outputs. So DGZ is going to be equal to 1. And you can see log 1 is 0. It's a largest possible value. But we are putting negative here. So it becomes the least possible value. We are still aiming for least possible value. Our goal is the same. It's just we use a different formula so that the training to be more stable. So this one is an actual pseudocode in a paper, and you can see that it is still using the wrong formula right here, even in a pseudocode. So back then, if you wish to do the implementation by yourself from scratch, and you are not very careful reading the whole text from a paper, you might miss the point that in the real implementation, they are actually using a different loss function for a generator. Because usually we just follow the pseudocode and translate the pseudocode into a real code. But it doesn't work in this case. You have to be very, very careful. And in DCGAN, it actually provides several guidelines to design the architecture. Because back then, it is difficult to actually design a convolution network that can be converged when we train it in a GAN architecture. So it is something. It is not easy. It is some real work. So it gives some advice. So after that, after we already have one working implementation, we can improve it, and have various of different implementations. That's easy. But the first one is difficult. The first working one is difficult. That is why I usually advise students to do the work. No matter how you can simplify your problem, or making it more dirty, but you need to have a working version. Even though it is not practical, it is not ideal, it is ugly, but you need to have a working version first, and you work from that working version to solve the issues, to getting a better one, and that is which is still working. Instead, a lot of people were doing something that trying to do a good implementation, an ideal for the ideal problem, and they are fail totally, and they try to fix the algorithm to make it work. It is not a way that people build things. People build something that work. Like people use some garbage that works, and try to make the garbage less garbage it needs. You're not doing some art that doesn't work. The garbage that works you can improve it to be a non-garbage or even becomes a very good product that works. But you very rarely you can improve art that does not actually works to become something useful. Also, that's pretty much happened for the development of GANs. After DCGAN has developed, a lot of different version comes up, and many of them are very different. But come up with the first one that actually works is something. It is something. So it is kind of a standard network, like you double the dimension of the height and the width, and if you double the height and width, you halve the channels. If you double the channels, then you halve the width and the height. For reducing the width and the height, you use sharded convolution, and for increasing the spatial dimension of increasing the width and the height, you use transposed convolution. All of this kind of layer, transposed convolution and 2D, transposed convolution 2D and the convolution 2D are now standard elements in PyTorch and the TensorFlow, and any of the coming frameworks for for deep learning. So here are some advice back like in 2015 or 16. A lot of different advice for building working architecture for GAN. So you can have it as a reference, but you don't have to follow these rules strictly. It just gives you some ideas or inspirations to how to modify your networks. There are more things you can do. So right now if I wish to design a GAN architecture from scratch for a certain dataset, what I'll do is just try to use my old implementation and to see what happened, and depends on the results. I will see the results and change the architecture according to this result, because I already know certain things happens because of certain reasons, maybe because of certain reasons, so I can change the design according to the result. But in practice, most of the time, right now you are just using the out-of-shelf networks and doing some minor modifications, like you're using a CycleGAN 2, maybe CycleGAN 3, and now you are using diffusion models to just do some minor modifications. But still, it comes handy when you need to design your own architectures. Okay, so let me explain how this trick is done, because right now you have already know that it is difficult. It's not straightforward for trained GAN models to extract things like what is smiling woman is, what is neutral woman is, and what is neutral man is. For one thing, it doesn't have the capacity of dealing with languages, and even if you can dealing with images, you cannot reverse an image to get the corresponding latent. At least it's not easy to do so. It is possible that if we're going to study to discuss the CycleGAN, you'll see some method to extract latent from one images to find a latent that match the image. But right now, because we don't have an encoder, so we cannot do. At least it's not designed to actually do so. So the things did in the DCGAN paper is that you actually just generate a bunch of images and pick the smiling woman from, like, if you generate 1,000 images, you might get like 50 or so smiling women, and maybe another 100 of neutral women, and maybe like 100 of neutral men. You simply find the latent of these images and average them, find the mean, and that mean is more likely than not to generate one averaging or typical smiling woman. And same thing, you can do the same thing for neutral woman and neutral man. So you get a representative factor for this class, and you can do this trick: smiling woman minus neutral woman plus neutral man to getting smiling man. So you can do this for almost every models, that image models as with latent, or even maybe sometimes even with a model with that is not image but some image with latent. For example, you can choose a bunch of image or face image that you generate. You can choose the younger man, younger people, not only younger men. You can choose a bunch of younger people and a bunch of older people, and you can calculate the vector of their mean, and then you minus the young. You use the old people minus the factor of older people to minus the young people. You get a new vector that we call it from young to old. Then you apply this vector to any latent of the. So you can generate one face and generate the corresponding face for the same face but that is older. So that's a popular trick. Although there are many different ways to actually to do this sort of things, to do more advanced tricks, but these simple tricks is a very useful baseline, and sometimes you may find it to be very, at least the quality generated is good enough for your use case. So let's talk about the conditional GAN. So one example back then I've used a lot is Make Girls Mom. The reason to use this website, it's very straightforward to introduce what the conditional GAN is. In this website, you can change the hair color, hairstyle, eye color, or maybe the whole styles of these anime girl images. So this is what the conditional GAN is. Not only you can generate a certain type of images, but also you can give a condition to control how the image is going to generate. So in this case, we can actually do things like this one. If you are labeling people with people in the training data with like smiling or woman or man or neutral, then we get this condition. Then we can do it directly without using this trick and do it more precisely. So this is an example of conditional GAN. The other one is if we are trying to generate MNIST, then a certain straightforward condition is the digit. So we can not only we can generate one digit at a time, or just a random digit. We can ask it to generate like 0 or generate 1 or generate 2. Also, that is what conditional GAN can do. So we are trying to, right now we are going to introduce 4, I think is a classic approach to this kind of things. So for the first one is conditional GAN. Okay, so I forget to, maybe it will happen somewhere, but I will get it later. So this one is conditional GAN. So basically, we simply, because first of all, we have to have we need to have a training data that is labeled. So like MNIST, we have a label for 0, 1, 2, 3, 4, 9 for a digit that the image is represent. So that's we need. Second, we need to modify this training architecture and generator and the discriminator a little bit. So for generator, we need to take 2 inputs. One is the class, so maybe it's a 1 hot, or other conditions like hair color, eye coloring. So, but no matter what it is just a vector. So we can simply concat it with the original latent. So that's no problem. We can feed it into G. So we can do a minor modification to the generator. For the discriminator, we can do pretty much the same. We have 2 inputs together. It will be a little bit difficult to deal with 2 different shape of input. But if you know how to do it, you have to do it one way or another. One way to do that is we simply we only deal with the image, and then we output a vector. And another part of this discriminator, we only deal with a class, and we output another vector. Then we do the dot product to this vector and get something. And this one is our output. That's one thing. So we can see that the class and the image match each other. The other way to do that is to we deal with the image first, and at the later stages, after we reshape the image into 1D convolution to do the densely connected part. In that stage, we include this class because the class is usually a one-dimensional vector. We introduce it into a later part. There are many ways to do that, but that's one of the difficult things because you have to do something to design the architecture. There are no one obvious or apparent way to do so. So other than that, it is exactly like what the unconditional GAN is. It's only that the only difficulty is how do we design the architecture of discriminator. The generator is usually a non-issue. It has an obvious and straightforward way to do so. Unless your class, your condition is not a 1D dimension condition, which we'll see that for the pixel to pixel case. So the other, let me correct we have this one. I think this one is the last one that I haven't correct yet. Okay, so another interesting use of this class labeling is semi-supervised GAN. So in this case, instead of to train a conditional GAN generator, we are using this label in another purpose. We're trying to sort of doing a semi-supervised training. So consider we have a training dataset like contain 1 million images, but to do the labeling is very difficult. So we only label like 1,000 images out of these 1 million images. It is very pity that we just discard this the rest of the image because it is a majority. It is more than 900,000 images. It is 999,000 images. We are going to discuss if we are doing it in a supervised learning way. So what we should do is we are including this unlabeled image along with labeled image together. Although most of the images are not labeled, we can still use our neural network to learn to extract the visual features from these images. So we are doing this semi-supervised GAN. So the thing is, we are going to do actually we are doing a multitext for our discriminator. It not only output whether the input image is real or fake, it also to do the classification. So for the generator, it does pretty much the same. We only modify the discriminator so it has another task to do. That is to do the classification. So of course, the training is look like something like this one. So for each batch, we take like 10 images that has label and the 10 image that has without label. So for the 10 image with label, we train it just like a normal classifier. And for the 10 image without label, we also generate 10 images from the generator and use this image to train the discriminator. And for a generator, the training is unchanged, just like the original unconditional GAN, because it is the unconditional generator. So that we can have the best of both worlds. It also have a benefit that it can prevent overfitting, because for 1,000 image, maybe you have 10 different classes and you do the classification. If you only have 1,000 images, it may be very easy to get overfitting. However, you are trying to do 2 tasks. It's not going to be that easy to overfitting because it has this weight does not have a single purpose to serve to fit the training data. It also has another purpose to do the discriminator to serve other 999,000 images so that it can do the job as a discriminator. So this kind of training, we can prevent this weight to default themselves to fit this 1,000 image. So that's why it can a little bit, sometimes very efficient to avoid overfitting. The other interesting architecture is involved GAN. It also has a discriminator and a classifier architecture. So we're going back to this guy later, semi-supervised later. Oh no, we are not going to that. We're going to this guy, DCGAN. We'll discuss DCGAN a little bit later, which is has some connection with this one, because you can see the architecture has actually pretty similar. Okay, so let's go back to InfoGAN. So the InfoGAN is that we don't actually have a label of an image, but we know it must have some labels. So suppose you got the images from MNIST. Suppose we don't have a label yet. So although we don't have the label, we can still see that, okay, this sort of images digits look like they are pretty much similar. And this sort of say that 1. those images are pretty similar. We can, if we really need to group them to get to do the clustering, we can in fact see the images of the digits ones are pretty similar. The digits of zeros are very similar. The digits of threes are, there are a lot of them are very similar. So there are some intrinsic labeling should be in there. So we are trying to do the clustering and sort of the conditional generating, automatic conditional generating altogether. So the things we want to do is we are trying to randomly generate the condition. And we also have some random latent right here and sending them into the generator. So instead of just have a discriminator, we also have a classifier. This classifier can classify the image that is given from the generator. So it is kind of strange. This guy is, I mean, the discriminator and the classifier are practically the same network. They only have a different output. But the discriminator is work against the generator, but the classifier is work with generator because it will help generator to generate something that's, and the classifier will agree with the generator that it generate this thing. So for example, if we have a discrete labels that have 10 categories, we actually have generate the latents here by using the uniform distribution to assign this 1, 0, 1, 2, 3, 4, 5 to 9 in equal chance. At the beginning, we actually don't know what we are generating, but no matter what we generate, the classifier agree with it. Okay, if you are using 0, it says, okay, this image we are characterize it as 0. So that's the info GAN. But the key idea of info GAN, you can see the info here is stands for information. The thing, the issue that the info GAN wish to solve is sometimes the generator does not use the latents efficiently. It will discard the information from the latent. So it wish to actually efficiently use all the information contains in latent, at least in here. So the generator, by using the classifier here, the classifier is what the classifier doing is to recover the latent. So by doing the latent to using the generator to do the to generate image and using the classifier to recover the information of latent, it basically ensures that the images, I mean the informations from here pass through here to the image and pass through here and back here without harm or without losing anything. So it makes sure these informations are important for image and we are not ignoring them. So that's the original idea of what info GAN is trying to do. So for AC GAN, the AC GAN is also a way to train the conditional GAN, but without the issue that we have to design what the architecture of the discriminator is, because it treats the class as the output, as a target instead of the input. So we have exactly the same discriminator architecture as before. We only need to have one more set of output, that is the condition, the class. So it is also a discriminator and class combination between the discriminator and the classifier. Or you can see it as a shear weight of the discriminator and the classifier. So The other part are pretty straightforward. The generator generates an image and sending to this guy. Okay, so the classifier, when we try the classifier, we simply train this part only. So it actually only train on the real data, on the real data. So that's how the classifier is training. For discriminator, it also, of course, it's training on the real data and generated data, because that's we need to have both, because so that we can have because it is a binary classifier, we have two kinds of category, so we need both of the category. So that's for sure. But for classifier, we only need this data, because that's all we need. So for generator, in addition to kind of cheat the discriminator, it also has to align with the classifier. You can say that it to achieve a high score from both of the discriminator and the classifier. So unlike the case of InfoGAN, the classifier, it doesn't have a dual personality. One is cooperating with the generator, and the other is against it. In this case, it only against with generator, but because the classifier doesn't even care about the input doesn't take an input from the generator. So we only need a generator to satisfy the output of the classifier. So we also provide some code, sample code in this same repo for DCGAN and conditional GAN. So it might be you don't have to modify anything. There used to be a homework to do so, but you don't have to, because we have a different set of homework. So, but you can still try it if it works. Because code is a little bit old, but you can see the architecture and try to do the same thing. It will be very interesting. You can see that you can actually generate these digits, and you can control what digits you can generate. So another type of conditional GAN is pixel to pixel. It is a kind of conditional GAN, but the condition is an image. So in this example, we are taking a image that consists only the edge part of the image, and we wish it to generate, the target is in the second row. We should generate a photo that coincident with this edge graph. Also, this one is also a show and also a show. So of course, it doesn't contain, the condition doesn't contain the enough information, because we actually don't know what this shoes, the color of this shoes might be. So it actually generates a totally different color. But we may think that the blue color is feasible. It's possible. We should say it's possible, because we have experienced that a lot of the shoes, like this one, running shoes like this one, may have a color of blue. So for the other style of shoes, the color may not be that different, but you can still see they are different, and all of these colors are sort of possible in this style of shoes. So this one is pixel to pixel. So this one is another example that we are giving a segmentation of this one and training with this ground truth, and in fact we can get the result. This one is taken from testing data, so the second row is not in fact fit it into the training, but you got an idea what the training data might be. So this one is another example we were doing, I think it's like 2 years ago. So this one is do the coloring. When given an edge images, just like the shoes. But we also can give another set of hint of coloring. So either you give a simple giving the edge image, or giving an edge image with some of a hint, like this one is a hint. Then we can generate a coloring image according to your condition. So that's the result for using. Basically, it's just a modified version of pixel to pixel. But considering about the setting, since we already have a image ground truth right here, and we have the input as a condition. So this is just a supervised learning, right? Because we have x and y exactly. So why do we even need GAN? Isn't it just supervised learning? So the thing is, okay, there are one more set of, this is real, this is fake. So the GAN actually plays some roles in this training, which we'll introduce a little bit later, of why this is important, or why it is necessary. But the thing is, if you are trying to use only the L1 loss or mean square error, it is a typical supervised learning. And you can try it without the GAN loss, the discriminator loss right here, which we usually call the adversarial loss. You can actually discard or remove this loss. It can still train, but we'll show it why we actually need this. But before that, we see what it is for a pixel to pixel training. So we have a usual L1 loss for the supervised part of it, but we have an additional loss function that is a discriminator. The training of this discriminator is exactly the same as usual GAN. It just, you can consider it as a GAN plus one supervised L1 loss, or you can consider it as a supervised loss, but with an additional adversarial loss. Both of them are very consideration, but they are just a combination of supervised learning and this adversarial loss. But why is this useful? Or not just say it's necessary. Why is the adversarial loss useful? Let us consider a toy example. This one is a toy example. We wish to convert a circle, a disk right here, into a square with the same area, with exactly the same area and the same color. So this one, it seems to be example, and we are expecting it should be easy to train, right? So what if we consider only the L1 loss? In fact, you can see the middle row is the ground truth, and the top row is the input condition, and the bottom row is the output of the trained model. So it is just like this one, except we don't have the discriminator at all. We only use L1. So you can see there's nothing wrong here. We have pretty much exactly what we want. So how about mean square error? We heard a lot of people saying that mean square error produce blur results, produce more blur images. But for this example, it seems totally fine. Every square is as good as what we get right here. So in fact, in this setting, we don't need the adversarial loss at all. There's no need to have the adversarial. There's no use at all. Let's just change this the problem a little bit here. So our input is still a circle with color fill in, and our output is still a square with the same color and the same area, except that sometimes the square rotate 45 degrees. The chance of rotate 45 degrees is totally independent to the conditional image. There are 50 to 50 chance to rotate or not rotate. So that's a small modification of the problem set. But this one is crucial because it demonstrates when do you actually need the adversarial loss. So let's see first for mean square error. You can see that the result is an average image of the two possibilities. So this one is the optimal result. If you are using the mean square error as the loss, because mean square error is worked at pixel wise, it doesn't have anything related to the structure of this square. So the best this loss can, if you are fitting this loss, the best the neural network can do is to minimize the loss, and this result achieve the minimal loss if we are considering mean square error. So if we are using mean square error, this one is the perfect result. So a lot of people, when they encounter a result that they doesn't feel like it, and want a different result, changing a different architecture by using, we're using a transformer or using a diffusion model or other thing. The thing is, it doesn't matter which model you use. You are already achieving the optimal result. Even if you use a GAN model, a fully optimal model, you are going to get this result. The only thing you can do is make it worse. You are going to use a different learning rate, different learning schedule, different model, and you failed your training, so you can get a different result. But if you are successfully training, you are getting this result because this one is the best you can get. So if you are using L1 loss, you are getting a square because mean square error is converged to the mean of things, and it's calculated for each pixel. So that's why we get the kind of a shadow of two squares together, because these are the average of the two possibilities. So but for L1 loss, it actually converges to the median. But for our case, the range of median is very large because it is either 0, half a chance it becomes 0, and half a chance it becomes 1. So that every value between 0 and 1 is possible if they are falling into the part of this half part. Half to be black, half to be colored. If they are falling into this part, they can be, the generator if this pixel is generated to be any kind of color, they will have the same loss value. So doesn't matter which it is. And why does it copy the original circle? Because it is easy for the neural network to do. If you are initialize the render neural network, or a convolutional neural network, it will kind of look like an edge detector. So it will, at the beginning, it will look some sort of like a circle. And this one, so it in most of the case, it will actually converge to something like a circle and circle shape. And to achieve the maximum, I mean the optimal value, it will have the same color. So that's why it will come up with something like this one. So how about if we add the adversarial loss in it? So we get what we want, the desired result right here. Although it is a little bit difficult to train, so you can see some defect here and there. But at least it is somewhat square with the same color. So because because we are using pixel to pixel and using the adversarial loss, this kind of thing does not work because the discriminator will reject this kind of image easily because they have something that is not straight. And they will also reject this one easily because they are something like some color in between colors. So they reject them easily. So that's why they can generate something like this one, because they cannot reject it easily. It only left that it cannot predict the randomness because it has half of chance to become the rotated and half of a chance to become non-rotated. There's nothing it can predict whether it is rotated or not. So it only need to generate the square with one rotation, because no matter no matter what the chance what is the probability of making it rotate or not rotate, there will be half of the chance it getting correct and half of the chance it doesn't get incorrect, I mean. So why bother? So it only generates one set of squares. Sometimes it generates the other way, but I mean, if you train it in another round, you do another training, it may generate a rotated square or non-rotated square, but it always only generates just one sort of things. Just pick one of them. So the adversarial loss do is if your target, your expected output is kind of has some uncertainty in it. There's like when we see in the show case, the show has a color, but the color is not. We don't have the information of color. It can be any kind of color. So instead of, if you are using the mean square error, it will generate the average color. If you are using an L1 color, every pixel it will generate a one rendering color. But you are using the adversarial loss with it, it will reject anything that is not plausible. It will only generate something that is plausible. So that it cannot help you to actually predict the uncertainty if that uncertainty is not predictable or very difficult to predict. But at least it will pick one for you. So that is adversarial loss can do for you. So if you encounter things or issues like this one, so you can consider of adding an adversarial loss to your architecture of training. So we have some tutorials on the pixel to pixel code. You can see that in the repo. So another interesting application or conditional GAN is CycleGAN. But in this case, it doesn't have the label. This one is the famous videos of CycleGAN. At that time, we already know that pixel to pixel, and a lot of people are using it, and it is become very popular. So when people see this video, our first impression is, okay, you are applying pixel to a sequence of images, and okay, we already know that pixel kind of lazy. Also, we can see that okay, they are consistent in each frame, so that's no surprise. But on a second thought, wait a minute, how did it prepare the training data? There's no way it can prepare a training data of a zebra and a horse, and they do the same action and pose, one frame by frame. We can imagine that if some guy is very rich and he has a lot of zebra and horse, and maybe he can use some way to do that, but it's kind of unlikely. In the setting of pixel, so either we can already have some images that corresponding to each other has already existed, or at least we have some method to convert images from A domain to B domain easily. Like we can translate a color image into a black-white image, and translate high-resolution image into a low-resolution images. So we can easily construct a data set. Of course, the other way around is difficult because, it is difficult to make a black-white image into a color image, and it is difficult to make a low-resolution image back into a high-resolution image. So that is also those kind of one way easy and the other way difficult is a perfect scenario for making training data for pixel to pixel. But this one is not the case because no matter making horse to zebra or zebra to horse, either way they are difficult. So how do we actually train it? It's sort of like the setting of InfoGAN, because InfoGAN are also trying to do a conditional GAN without actually the labeling. So this one is kind of some similarity between to the InfoGAN. So let's see how it does. Also, this one is another example that we do like 5 years ago, I think, or maybe even 6 years ago. So this kind of data set, you can see that it cannot, well, we are very difficult to actually prepare training data for pixel to pixel algorithm. But one thing you need to, we can observe is the hair. Not only it has a texture, change the texture like the zebra and the horse, it also kind of modify the shape, because you can see that it has a short hair for the male image, but for the female image, when translate into a female image, it has a longer hair. And this one is a little bit low quality, but it attempt or try to remove the hair, but remove something is usually more difficult to do. This one does not remove the whole hair entirely, but it actually try to remove some part of the hair. So this one is also another example of using CycleGAN. Okay, so the setting is for the pixel to pixel setting, we need paired data, and for another type of question, we only have unpaired data, and in many cases, it is very difficult to prepare the paired data. So how does CycleGAN to do that? In fact, we do not know what is the criteria or requirement to have the perfect solution. What does it mean to have the translation between one pair to X to Y if they are not paired? There are many possible things. If you only give two set of images in two domains, and you wish, so you say that we wish to translate image in one domain to another. The question is not well defined. There might be many different way to do the translations. So in CycleGAN, it actually, at least it sort of try to more specify to or ask a question more explicitly to some extent, not entirely, but try to do it more explicitly. So it does, what it does is, okay, we have actually two generators. One is from X domain to Y domain, and the other is from Y domain to X domain. So the first requirement is we wish GX, the output of GX is something similar to Y, and the output of the FY is something look like X. So if X is horse, Y is zebra. If we put a horse into the generator and get something output, we wish it to look like zebra. And if we put some zebra in this F generator, we wish it to output some image looks like a horse. Okay, let alone, this requirement alone can already produce some kind of translation power to do image translation. Because like what we have seen in the circle case, we know that uninitialized generator, it works kind of like a edge detector. It works like an edge detector. So it will naturally kind of preserving the architecture, the structure, the structure of the original images. So this requirement alone is, sometimes it is enough to do the domain translation for these images. So for example, like the zebra and the horse, it might just simply work. However, this, if we can have more things, then we can have more successful rate to do the training. So in fact, we have one more conditions that is easily available. That is kind of like in CycleGAN. We wish that the generated image to preserve certain information of the original images, like the structure. So we can allow, we are expecting the color or the stripe of the zebra are lost when we generate it become a horse. But we are kind of still hoping the structure of the zebra are preserved into this image. So like in CycleGAN, we do a classifier to extract or to recover the original images. So it does seems like this GX translate the horse into a zebra and then translate the generated zebra into a horse. And we wish these two guys to be the same. And vice versa. When we put a zebra into F and generate a horse, and using a G to convert, to recover this zebra back to a horse, this one zebra and this one is horse, and recover this horse back into a zebra, we wish it is kind of equal to the original one. So I put an equal sign here and put the same notion, same symbol right here, because this is our goal. We wish them to be the same. Or you can see the diagram here. This one goes here and then this one goes back. We wish this one to be as close as possible. The loss between these, the difference between these two guys, we call the cycle consistency loss. And of course, for the similarity, we use the adversarial loss. So that's the whole idea. So For the training, we start from input image, and of course, we are feeding it into a discriminator so that it can tell the difference between the generative one and the real one. This one's the real one. And we go to a generator from A to B. And so here we get a zebra. And also we feed it into a discriminator as a fake image input. And then we go back to this generator and get the recovery, the contrast image. And we hope we have another loss between these two guys. Maybe L1 loss, I will say L1 loss between these two guys. So that's our whole training. So in fact, we have two different kinds of loss. One is adversarial loss. So we have two discriminators. We have two sets of these guys, and we have the cycle consistency loss. We have both of them, and use L1 loss, and then that's it. And then we put them all together. So that's our whole training algorithm together. For the network architecture design, in the original pixel to pixel, it used UNet. It used a UNet. UNet is a very popular network. So you can simply search UNet. U is the English letter U, and net is a network. Or you can see our repo. You can find out the simple implementation of the UNet. But in the CycleGAN, it considers two architecture. One is the UNet, like pixel to pixel, and the other is this encoder transformation decoding. This one is also used a lot, but you don't have to use this one. For the CycleGAN, you can still use the UNet architecture. It works just as good in most of the case. Only if you wish, you don't want to keep the structure. If in my experience, if the structure of the original image and the target image are pretty much aligned, then you are better using UNet to achieve better result. The only thing that you might try to use this one is you may want to use this one is they have totally different structure. Maybe they have a different shape, or maybe they are in different positions. You may want to use this kind of architecture, so they are not that shape dependent. Okay, so other than that, pretty much. And so these are some examples taken from the paper. Although I still think my gender swapping example is a little bit better because they have a different shape. Because you can observe that most of these cases are kind of just texture transfer. That still looks good, to be fair. But back then, there are already a lot of different algorithms that can do sort of texture transformation pretty good. So this example doesn't emphasize the strengthness of CycleGAN not enough. But still, they are very typical and good. And the horse zebra video is stunning. It's very good. But in fact, CycleGAN, if you are using, especially if you are using this kind of architecture, you can have a very dramatic transformation between one domain to the other very different domain. So this one is also the very typical usage for using for the CycleGAN. They can do very well. This one, although I say that this one doesn't emphasize the full potential of CycleGAN. But if you are focusing on this kind of like texture, more or less like a texture transferring, CycleGAN can do very well, or can do very well. Like the art style transfer, it can do extremely well. For like this one shows. Just what I just said, it was that it can actually, this is not the only case it can do. It can do more. Okay, so we also provide a simple implementation in our tutorial. So if you are interested to try it, you can use our implementation or use other like 20 or 30 other implementations. They can do it good. So that's it for our lecture this week. We're going to continue to talk about more about the GAN, like style GAN and other WGAN and SN GAN next week.